In this video, we're going to talk about rotational motion. So rotational motion is typically when we start to study, so we begin the study of rigid bodies. So up until you get to rotational motion, you're considering all of your objects to be particles. So when we drew free body diagrams, for example, we drew all of our forces acting at a point. And the thing about particles is that they cannot rotate because they're one-dimensional. So rigid bodies are now extended objects. So they're extended into 2 dimensions or 3 dimensions, but we'll only look at 2-dimensional rigid bodies. And they're extended objects, so extended objects whose size and shape stay the same. Okay, so size and shape do not change, and that's why they are rigid. So they do not change. So particles cannot rotate, so sometimes you're tempted to think that they can kind of spin, but they need to have an axis to spin about, and if they're one-dimensional, then that axis doesn't exist. That axis has to extend into another dimension. So they cannot rotate, but only translate, while rigid bodies are allowed to rotate about some axis. Okay, so now let's talk about rotations and how we study rotational motion. So I'm going to draw a circle, and say, for example, we have an object that's moving on the edge of this circle. And it starts at some point in the edge, and the circle has a radius r, and then it moves through some angle, so call it some angle theta. Again, this is also r. Everywhere on the circle is the same distance from the center. So if it rotates through this angle theta, then this length along the edge we'll call s, and this is called the arc length. So the arc length is the path that you travel, or the distance that you travel when you go in a circle or circular motion. And our angle theta, we're not going to typically use degrees to measure it, but instead we're going to define the angle to be the ratio of our arc length to our radius. And so when we have the case where s is equal to r, so s is equal to r, so theta is just 1, we're going to call that angle 1 radian. So this is the definition of 1 radian if you've ever seen it, or if you've ever used radians in a trigonometry class or somewhere. And you can use this, this definition to find the number of radians in a full circle, which you might know or might be familiar with. So for a full revolution, so if you have an object that moves along one full rotation of a circular path, then theta is equal to the arc length over the radius. And the arc length of a full circle is just its circumference, or 2 pi r. And then you divide by r, and these r's will cancel. And so you're left with 2 pi radians. Okay, so you may know that in a full circle, or 360 degrees, that's equal to 2 pi radians. And this formula is how you use it, or how you find this. And then if you wanted to see how much a radian was in terms of degrees, to give you some intuition, then there are 360 degrees for every 2 pi radians. And so if you punch that in your calculator, you find that 1 radian is 57.3 degrees. Okay? So now let's move on and talk about angular displacement. So let's draw another circle and say that we start at some angle. So typically we start measuring from the positive x-axis. So this is where we typically start measuring our angle theta. Okay, so imagine we start off at some angle that's not quite at the x-axis, so this we'll call theta 1, and then we rotate up to some other angle, theta 2, so maybe we start here and end here, going through this arc length. Well, then we can define the angular displacement just like we would the displacement for linear motion. We can define that to be delta theta. And so delta theta will be our final angle, theta 2, minus our initial angle, theta 1. Okay, and now I moved counterclockwise, so I need to define what I mean by positive and negative. If we move counterclockwise around a circle, then this is going to be associated with positive motion or a positive angular displacement. And then if we move clockwise, this will be a negative angular displacement. Okay, and then just for some language, sometimes we say moving through an angle. So moving through an angle, or sometimes I call it sweeping through an angle. We call this subtending. So if you see subtending an angle on a homework problem or something like that, that just means it's the angle that you move through, and it's referring to the amount of angular displacement. So now we can talk about how fast we move through this angle and derive analogous quantities to velocity and acceleration, but in angular variables. So our average angular velocity, so this is going to be a Greek omega, and it's going to stand for angular velocity. Okay, so it's not a W, it's a little bit more round. So this is an omega. It's angular velocity, so it's going to be the change in our angle over the change in time, or theta 2 minus theta 1 all over t2 minus t1. And we can do something similar to what we did in kinematics. So this is the average angular velocity, but if we wanted to get the instantaneous angular velocity, this would just be theta over t. And here we had to use a little bit of calculus where we let this interval delta t tend towards 0. Okay, so you don't need to know calculus, but this is what you get when you take this limit. And so on the right we have instantaneous angular velocity. Okay, and then on the left we have the average angular velocity. And we can do the same thing for acceleration. So for angular acceleration, instead of A for acceleration, we're going to have alpha. And alpha average will be the change in omega, or the change in angular velocity, over the change in time, or again, omega 2 minus omega 1 over t2 minus t1, where alpha is our angular acceleration. So we'll always use Greek letters for our angular quantities, and this is a Greek alpha, a lowercase alpha. And we can likewise define the instantaneous acceleration as just alpha equals omega over t, again taking the limit as delta t tends towards 0. And so these are our instantaneous quantities. And then we have our average quantities, just like we did in kinematics of linear motion. So if we assume constant angular acceleration, then we can do something similar to what we did in regular kinematics. So in regular kinematics, or linear kinematics, we defined some kinematic equations based off the assumption that our acceleration would be constant. And so I'm going to write those kinematic equations and then show you what they turn into if you make the exact same arguments for the linear variables and linear quantities, or rotational quantities, I'm sorry. So these are I'm going to write the 3 kinematic equations. If you've seen the other two, then you can replace the linear variables with the angular variables for those as well. But often in general physics, you only see two kinematic equations, or three kinematic equations. Okay, so these are our three kinematic equations that we solve most of our problems with. And if we made the same arguments, assuming constant angular acceleration, we would get analogous equations of angular variables. So instead of v, we have omega for angular velocity equals the initial angular velocity plus the angular acceleration times time. And instead of position, we have an angle, so theta equals theta naught plus omega naught times time plus 1/2 alpha t squared. And then we get omega squared equals omega naught squared plus 2 alpha theta minus theta naught. So here we basically took all of our linear variables and turned them into angular variables. So x became theta, v became omega, and a became alpha. Okay, so now let's look at some relationships between our linear quantities and our angular quantities. So we can start by looking at our average linear velocity. So first, let's imagine we're going in a circle again. So we're at some radius r of this circle. And we know from kinematics that our velocity, our linear velocity at any point during our motion is tangent to our trajectory or tangent to our path, meaning it's just going to touch the path at one point. So if you're trying to draw the slope at the point where you are in the path, that is the direction of your velocity. So your velocity is tangent. That means that this distance that you're traveling is going to be the arc length. So we have the velocity is our distance, or change in distance, over change in time. Okay, well, we said before that delta s, that's just r times theta, but if s is changing, we know r is constant for a circle. The radius is the same everywhere. So for delta s to change, that must mean we're moving through some angle delta theta. Okay, so we replace delta s with r delta theta, and then over delta t. Well, this delta theta over delta t is just omega. So we can replace that, and we get v average equals r times omega average. Okay, and then we can make a similar argument just like we did for our instantaneous quantities before to get v equals r omega for the instantaneous velocity as we're going around the circle. And it's important to keep in mind that this is our velocity that is tangent to the circle of motion. Okay, to the circular motion. So sometimes you will see this written as v sub tan equals r omega, just to remind you that the velocity is tangent to the circle so you know which one you're talking about. Okay, we'll draw a circle again, and now we'll consider the case, what if we are speeding up or slowing down, so speeding up or slowing down, while we're rotating, so while we're going around the circle. We didn't consider this when we looked at uniform circular motion because we said that uniform circular motion occurred when you had a constant speed. So going to be somewhere on the circle, and now I'm just going to draw my velocity. I know it's tangent, and if we're going in a circle, that must mean that there is some acceleration inward that's changing our direction. So this is radial acceleration. So we already looked at this when we looked at uniform circular motion and centripetal forces. But if our tangential velocity is increasing because we're speeding up, then that must mean that there is a component of acceleration that is in the same direction as our tangential velocity. So we'll call that a tangent or tangent acceleration. There must be some acceleration that's in the same direction as v in order to increase it or decrease it. Okay? So if acceleration and velocity are in the same direction, then the velocity increases. If it's in opposite directions, then velocity decreases. And if they're perpendicular, then that changes the direction. Okay, so there must be a component that's also tangent to this circle. Well, what we can do is, since the tangent component of acceleration is always going to be perpendicular to the radial component of acceleration, we can treat these kind of like they are xy components. So we said that we can always form a right triangle of any vector by going some amount to the left or right in the x direction, and then some amount up or down in the y direction. And we can do something similar to here. So x and y are always perpendicular. That's why you can always create a right triangle. And so now we'll always be able to create a right triangle out of our tangent and radial acceleration, which means they can kind of serve as components to our overall acceleration. And if we want to combine these into a single acceleration vector, we can do that just by using the right angle math that we already know. So we can use the Pythagorean theorem to get the magnitude of our acceleration just by doing the square root of the tangent acceleration squared plus the radial acceleration squared, and then taking the square root. And so if you combine these, you would get a net or overall acceleration that was somewhere kind of in between these two. Okay, so if you imagine drawing one and then drawing the other, so you could do your parallelogram rule, your overall acceleration would be somewhere between your radial and tangential acceleration. Okay. So how do we find the tangent component of acceleration? Well, we can look at changes in our velocity. We said our velocity is equal to r omega, but r is not going to change. So that must mean that our omega is changing. So if we're speeding up, going faster around the circle, we must have a faster angular velocity. Likewise, if we slow down, our angular velocity must also decrease, while our radius stays constant. And if we divide by delta t on both sides, then on the left we have just average acceleration, delta v over delta t. And on the right, this quantity, delta omega over delta t, that's just the average of the angular acceleration. So this becomes r alpha average. And similarly, you can make an argument to get your instantaneous acceleration, and you get a equals r alpha. So now we have the tangent velocity is equal to r omega, and the tangent acceleration is equal to r alpha. And then don't forget, if we want to get a radial, then the radial acceleration is just v squared over r, but we can use this relationship to turn this into something as a function of omega. If we plug in r omega for v, we get omega squared times r. And then now we can find radial acceleration and tangential acceleration. So now let's talk about rotational kinetic energy. So when we talked about work and energy, we said that any object that's moving has an associated kinetic energy, an energy associated with that motion. Well, even if something's not moving left or right or up and down, it's not translating. If it's spinning or rotating, that's a type of motion, so there must be some energy associated with it. So if we imagine we have some disk, so this is not a hoop or anything like that, this is a solid disk, and say we pick just a particle, so Single particle, we'll call it particle A, somewhere along the disk, and it is some distance RA from the center, so it has some radius. And as this thing spins, as this disk spins around, this particle is also going to go around in a circle. Okay, so its circle is going to have a radius RA, however far away it is from the center. It's going to spin with some angular velocity omega. It's also going to have a velocity that is tangent to its circular motion. So the velocity of A will equal RA times omega. So now we can write the kinetic energy of this. So we would typically write 1/2 mv squared, so ma va squared. But if we substitute m for the velocity, we get 1/2 ma ra squared omega squared. Okay, so this is the kinetic energy associated with the rotation of that particle in terms of angular variables. Okay, and one thing I want you to notice is I didn't put a subscript on omega. Okay, so both our velocity and the radius are going to depend on the particle. So the particle that we chose, particle A, it's going to depend on where it is, and if I pick a particle that's further out, then as the disk spins, it has to travel farther. That means it has to go faster in order to go that longer distance in the same amount of time. So V and R are going to depend on where you are. The outside of the circle is moving faster, has a faster linear velocity than a particle closer to the center. It also has a larger radius. But omega is the same for all particles. Okay, so when one particle completes a complete revolution, then all particles will complete a complete revolution. And so omega must be the same for all particles, where V and R might be different. So they get their own subscript to denote which V and which R we're talking about. Omega is going to be the same for all of them. And that means if we want to write the kinetic energy of this whole disk, then we need to look at every particle. So we have 1/2 ma ra squared omega squared. And we'll do the same thing for some particle B. Okay, and we would do it again for a particle C, and so on. And since there's 1/2 in omega squared in all of our terms, we can factor those out. So if we do that, we get 1/2, and then in parentheses, ma ra squared plus mb rb squared plus ... And then we get our omega squared. So we want to call this quantity in parentheses, we're going to call it I, which stands for, or is defined to be, the moment of inertia. And so now, if we call all of this I, this is going to become 1/2 I omega squared. Okay, so we have K rotational. So this was the kinetic energy of a disk that's rotating. It wasn't translating, but we got 1/2 I omega squared. If we compare that to what we got before when we were considering particles that were translating, we had 1/2 mv squared. Okay, so this was kinetic energy of translations or linear motion, and this is the kinetic energy associated with rotations. Okay, so if you notice, these look very similar. We have an angular velocity squared and we have a linear velocity squared. And instead of mass for rotations, we have moment of inertia. So mass gives objects inertia, which is their resistance to changes in their motion, resistances to acceleration, or changes in their velocity. The moment of inertia will play the same role but for rotation. So it's analogous to mass, but for rotations. So plays the role of mass for rotational motion. So what that means is if I increases, if we have a larger I, that's kind of like having a larger mass. It's harder to get something moving. So if you have a larger I, it's more difficult to get something rotating. Okay, so more difficult to start or stop rotation or change the angular velocity. So harder to change angular velocity omega. If you have a lower I, a smaller moment of inertia, that means that it is easier. Okay, so it's easier to get something to rotate if it has less moment of inertia that's resisting those changes to its rotation. So let's talk a little bit more about moment of inertia. So we said I was defined to be the moment of inertia. So you think of mass as what carries inertia, and then you have moment of inertia for rotational motion. It has units, if you go back to our equation before, has units of kilograms times meters squared. So that was our m times r squared. And moment of inertia is a scalar quantity. So it's not a vector, it doesn't have a direction, and it is always positive. Okay, it's always positive because mass is always positive, and even if our distance r is negative, it's going to get squared and become positive. So now let me just write the equation again really quick so we can look at it. MARA squared MBRB squared plus dot dot dot. R is defined to be the perpendicular distance between our mass m, so between the mass and the axis of rotation. Okay, so that's really important. And what that means is, if we change our axis, we change our r, thus changing our moment of inertia. So a single object, and this is a important difference from mass. Once an object has mass, or you know the mass of an object, it doesn't change no matter where it is or how you measure it. But a single object can have different moments of inertia. So it can have a different moment of inertia. So I'll just say a different I, depending on the chosen axis of rotation. Okay, so if you choose to rotate your rigid body about a different axis, it may be easier or harder because your moment of inertia will change. So let's look at common shapes and moments of inertia of those shapes. If we were to have a rod like this, we could rotate it about the center, and that would have a moment of inertia of 1/12 times the mass times the length squared, where this distance is the length. But then if we take that same rod and we were to rotate it about this axis on the edge, so here we would be spinning it this way about this axis, but here if we spun it in a larger circle about an axis next to the edge of the rod, now the moment of inertia is 1/3 ml squared. Okay, and these moments of inertia are typically found in a table, and you can calculate them using calculus pretty easily. But if you don't know calculus, these have already been done for most generic shapes, and so you typically just go look it up in a table. And so if we had some plate, for example, that was had a width A and a length B, if we were to rotate this about its center, so we were to spin it about this axis, here the moment of inertia would be I equals 1 over 12 times the mass times A squared plus B squared. But if we take this same plate and we were to rotate it about its side, so an axis along the side of it, so we were to rotate it like this, then the moment of inertia would be 1/3 ma squared. So again, our distance A would be this. And so these are shapes that you would typically look up. There are 3 common ones that we use in problems quite often. So that is a cylindrical shell, sometimes called a hoop. And so if we were to rotate about this axis, so we were to spin it about this axis, running through it, the moment of inertia would be mr squared. If we were to take a solid rod or solid cylinder, sometimes called a solid disc, depending on how thick it is or how tall it is, then we rotated the same way, then the moment of inertia would be 1/2 mr squared. And then if we took a sphere and we were to rotate it about its center, then the moment of inertia would be 2/5 mr squared. Okay, so these are all ones that you would look up in a table or they would be given to you. But it depends on not only which axis you've chosen, but how the mass is distributed about that axis. So the moment of inertia isn't the same once you have an object. It doesn't stay the same. It also depends on the axis that you choose for that object to rotate about. So we've talked about kinetic energy associated with rotations, but what about the potential energy of a rigid body? So we'll consider gravitational potential energy. Well, if you have some rigid body, it's just some object, then this object's made up of a bunch of different particles, and if you were to change its height, then they would all gain some potential energy. So you would have particle A would have mass A times gravity times its height, Ya, that would be its potential energy, plus the potential energy of particle B would be mb times g times its height, and so on. But notice that g is the same for all of these, so we could factor it out. So this is ma ya plus mb yb plus ... all times g. But this, if you remember from our center of mass video, this is just the center of mass. So this is just the total mass times the center of mass in the y direction. So that means we can replace this and write the total potential energy or gravitational potential energy for the entire rigid body is just the total mass times gravity times the height of the center of mass. Okay, so the center of mass and the total mass determines the total potential energy, and we get an expression that looks very similar to the one that we already know. So let's talk more about kinetic energy. So if an object is rotating about a moving axis, so not only is it rotating, but the axis itself is moving, so that means it is also translating, then your total kinetic energy is going to be a combination of the 2 types of kinetic energy we saw before. You're going to have both translational kinetic energy and rotational kinetic energy. So that's going to be 1/2, and this is a rigid body, so I'll use capital M. And that axis, we're going to say that it's rotating about its center of mass, and its center of mass is translating. So it's 1/2 times the mass times the velocity of the center of mass squared plus 1/2 I omega squared, where we take our moment of inertia about the center of mass, times omega squared. So this is the translational kinetic energy and the rotational kinetic energy. And so now let's look at some different types of motion that you could have for a rigid body like. So let's look at the types of motion for, let's say, for a round object, because this is kind of more intuitive. So say you have a round object that is sitting on a surface. Okay, so first you can have the case where it is sitting still. So we also call this being at rest. Well, then your kinetic energy is just 0 because you're not moving. Well, then the next easiest case is if you're translating, so it's moving left and right or up and down. If it's moving across the surface, then this may also be called sliding. Okay, so sliding is another word for translating across the surface. Well, then you just have translational kinetic energy, so 1/2 mv squared. Maybe I'll make that capital M. Or you could just be rotating. So maybe you're rotating or spinning in place. So maybe you're slipping. So it's kind of like your tires are, you're spinning your tires and they're spinning in place, but you're not actually going anywhere. So that just means you have rotational kinetic energy. So you have 1/2 I omega squared. And then finally, you can have a combination of the two. So you can be translating, so moving left, right, up, down, back and forth, and rotating at the same time. So the most common example is if you're on a surface, this is rolling. And specifically in problems, it's often worded rolling without slipping. Because if you're slipping, it means that you're, it's kind of like your tires are spinning and you're not moving forward. You're slipping as you're trying to move forward. So you're not actually going anywhere. So rolling without slipping means you're not only rolling, but you're also moving forward. So your total kinetic energy is the sum of your translational kinetic energy plus your rotational kinetic energy. So I hope this has helped you understand the basics of rotational motion. And in the next video, we'll be going into problems where we apply all of these equations and use them to actually solve problems.